Oke, bismillahirrahmanirrahim.
Udah start ya?
Ya.
Manual cek,
Manual oke.
stabilize cek.
Jelas oke.
Stabilize oke. Bismillahirrahmanirrahim.
Oh,
Auto. In 3, 2, 1.
2, 3, 4, 5.
Apa gitu? Udah.
Suara sinyal lepas.
Oh. Landing approach. Lurus ya.
Jangan.
Hah?
Aman.
Oke. Oke. Manual mode.
Cut.
Disarm.
Our team is composed of 10 members with each a specific role and capabilities relevant to their mission. We divide each member into segmented missions, such as advisor, which is responsible for providing guidance and related experience, team leader, which is responsible for project strategy planning and team coordination, mechanics, such as airframe aerodynamic and modularity design, simulation and analysis, material selection and manufacturing, pre-flight mechanical check, and pilot. Electronics, which is divided into avionics and propulsion, telemetry, receiver, and video transmission. Software, including image processing, object detection, and dropping algorithm. Non-technical jobs such as administrative and financial management, and the last one is creative media management.
Our airframe uses a dual-motor, single-boom tail design with allowing a detailed configuration. The airframe has been optimized to make it more compact and light while still retaining its flight performance. The final design is shown in 4 points of view: front, right, top, and perspective. We designed the UAV to be easily disassembled and attached, making it very modular and easy to carry. The following is the detailed sizing of each part of the UAV. The UAV has a length of 1120 mm, reducing 16 mm from previous design. The details are set at 120 degrees, which both are connected to a 3D printed hub. The UAV wingspan is 1408 mm and keep the same NACA 2312 airfoil. Some adjustments were made to increase the UAV stability during flight missions and also to provide sufficient space for every systems component inside. For the payload mechanism, we increased the length to 65 mm to fit the body segment and slightly reduced the height to 16 mm in order to keep the 3D printed material from damaging while performing belly landing. As we adjust the size and dimension of the UAV, the empty weight is also changed from previously 1,586 grams to around 1,700 grams. The details are shown in this table. We analyzed the balance parameter of the UAV by calculating it using the center of gravity calculator, which will determine the mass distribution. Based on our wing configuration, we obtained 62.5 mm from the leading edge as the AC value. We use that AC value as the reference point for placing the electrical components. The reference points also give us the mass distribution, which is represented in the shown balance table. The storage box diameter is approximately 36 cm and 72 cm height. The internal structure is made out of PVC pipe and cut plywood, which is then glued together using strong glue, while the outer layer is covered using a 1 mm clear plastic sheet. Finally, the lid is secured using 3D printed threaded locks. Before fabricating the main airframe, we laser cut plywood sheet to create precise profile templates based on our CAD design. These templates are then sand-handed to ensure smooth outer edges for the hot wiring process. The primary manufacturing process begins by sectioning raw styrofoam blocks using hot wire cutter. To form the individual aerodynamic segments, the prepared plywood templates are secured to the side of each foam block, acting as a guide for the hot wire. Once all segments are profiled, they are aligned and joined using a foam glue. After the main structure cures, specified sections are modified, such as cutting out a compartment to create the airframe lid. Then, we cut the wings mount, which will be joined together along with the main fuselage later. In addition, we also create a hole for the spark tube and the electronics connectors. We apply the same hot wire cutting method to fabricate both wings and tails. However, to handle the high aerodynamic loads on both wings, we add structural reinforcement during assembly. Between the individual wing segments, we add a laser-cut plywood and stick them using strong glue. Additionally, a carbon fiber strip and a small amount of peel resin is embedded to act as an additional spark, significantly increasing the wing stiffness and overall structural integrity. Each part is then covered in a composite of clear resin and fiber cloth for extra durability and endurance. We carefully apply the resin to ensure it covers the entire surface. Finally, we let them dry for the best result. For detailed components such as tail hub, motor mounts, and camera mounts, and few other parts, we 3D printed them using PETG filament. To install every component, we either use superglue or adhesive epoxy. After each part is installed, we carry out a few tests to ensure each connection is safe and secure. As for the ailerons for both wings, we attach them using strong tape, while both tails use a 3D printed connector, which is then glued together, followed by a basic movement test. After that, we cut a precise hole for the aileron servo. Finally, we install a plastic wings horn to the ailerons and apply strong glue. We design each connection in a way that makes assembly easy, such as applying a simple sliding lock for the wings and mounted servo pin on the edge of the tail tube. This assembly process took around 2 minutes for 2 people. The payload system uses an internal gravity drop configuration secured by a servo pushrod locking mechanism. A payload is locked on a vertical mount, held in place by an extended pushrod acting as a mechanical stopper. The servo rotates and retracts the pushrod via a horn linkage, releasing the payload purely by gravity. After the designing process, we 3D print the design using PETG filament for the stiffness and impact resistance. After that, we install the servo and its arm, and finally insert a metal rod to the arm before sticking the entire piece into the airframe using strong epoxy glue. We also changed the servo from GX1109MG to MX-ES08NA. The main reason for this swap is the transition to full metal gear train. This configuration delivers highly reliable, consistent torque under aerodynamic loads, while effectively preventing gear stripping and mechanical binding. The entire design was made to make both payloads stay rigid in a shaking vibration environment during high maneuver flight, while still easily released without any delay for more accurate dropping timing.
The main power source is a 6S2200 mAh LiPo battery. The battery is connected to a power module with split power to Pixhawk 6C mini flight controller and to a T-Motor 4-in-1 ESC in the back. However, between them is a safety switch which also acts as a circuit breaker. We soldered 6 AWG18 cables, 3 for each motor. We add an MR30 connector in the end of this AWG cable to make an easy plug-and-play mechanism which connects the AWG cable on the wings, which later connects the motor using a similar mechanism. The output pin for the ESC is connected to pin number 6 and 7 on the flight controller. This method is also used for both aileron servo on the wing, which uses AWG22 cable, and use black housing connector, which we use for all servo. 2 servos on the tail use this 6 to 4 pin extender, which later will be inserted and glued to the carbon tube. Other 2 servo is serving as the payload dropper, which connected the pin number 2 and 5. We split the power distribution to power the Raspberry Pi and the VTX by using UBAC with max current 8 amperes. This system is equipped with 2 switches apart from the safety switch, one for the Raspberry and servos, the other one is for the VTX. We designed the system in order to save power consumption. The flight controller is connected to 2 external modules, M10 GPS module and ELRS receiver module, which act as both the receiver and telemetry. The camera is mounted on the nose and connected to the Raspberry Pi using USB to C data cable. The Raspberry Pi 5, which is the onboard computer, is connected to an HDMI to AV converter module to convert the video output, which will be transmitted by the VTX module. We also use external VTX antenna for better transmission. The connector used is RPSM connector.
Upon booting, the Raspberry Pi runs the main script automatically. The first process is waiting for the heartbeat or connection from the flight controller. For every communication between Raspberry Pi and flight controller, we use PiMaveLink library since it's more practical for the mission. Synchronously, the flight controller is connected to the ground control station on Mission Planner software. This is where the autonomous navigation is set, which is later execute and loop according to the mission needs and conditions. For example, the main script will loop the waypoint if there is still payload on board and terminate the waypoint loop to immediately perform landing if both payloads have been dropped. We use a mounted webcam to capture on a video, which is later processed by the script run on the Raspberry Pi. As for the image processing algorithm, we use a simple Python script using OpenCV library, which detects the target based on the suitable color threshold for both red and blue color, and only accepts a 4-vertex polygon as the valid target while still being able to detect other polygon shapes. The camera will be enabled as soon as the Raspberry Pi receives a heartbeat from the flight controller. In this state, the program only enables the camera detection function while disabling servo drop function. However, after the UAV reaches a certain waypoint, the script will enable the dropping function so that as soon as the target is detected, the corresponding payload will be released. It can be seen here that while the detection program is running, the servo will not moving since the servo function is still in disabled mode. However, after being enabled, the servo will move if the target is detected. The payload dropping timing is calculated using free fall motion formula with additional delay, which is counted using the speed data of the UAV upon reaching the target area. For example, at high speed, the payload will be released earlier than when the UAV cruise speed is lower. To guarantee flight safety, every fabricated airframe is tested before final integration and field operations. This ensures that the airframe stiffness and load-bearing integrity match the requirements before the aircraft hits the runway. Initial test begins with testing the newly made airframe to simulated load and impact. The airframe managed to maintain its structural integrity after being dropped from various heights, while also passing the load test after enduring wake without any structural failure or permanent deflection. Before control surface check, we make sure that both wings and the tail electronics connection works perfectly by switching the pitch and roll while removing and installing both parts. Once all individual components pass their structural validation, the UAV enters the final integration and assembly phase. In this state, we conduct pre-flight actuation checks. By commanding every flight maneuver through the system, we systematically verify that all radar vector and aileron act accordingly. We perform a bench test using a digital electronic scale to measure the exact thrust output in grams. This also includes a small power consumption test where we can instantly monitor the real-time voltage drop and current spikes to verify the battery and the AC stability under load. Second, prior to launch on the field, we do a live on-spot structural pull test to confirm that the real-time thrust is actively pulling the airframe forward and upward.
We analyze the wings aerodynamics, which applies NACA 231 to airfoil in XFLR5. The result confirmed a stall angle of 13.8 degrees and a peak of CLCD ratio of 21.45 at a 2-degree cruise angle of attack, ensuring high efficiency during flight. Operational feasibility is further validated by a calculated minimum turning radius of 22.9 meters at 20 meters per second and 45 degrees bank angles. These performance characteristics are verified through high-fidelity 3D simulation in ANSYS Fluent to ensure accuracy across the complete flight envelope. Evaluating the aerodynamics characteristic at an angle of attack of 15 degrees, the XFLR5 results indicates that the configuration has entered a stall region, where the lift coefficient reaches its maximum and begins to decrease, while the drag coefficient increases significantly. This behavior agrees with the CFD result, where significant flow separation over the upper surface of the UAV center body reduced the flow velocity behind the fuselage to approximately 0 to 16 meters per second, forming a low energy wake. Several wake regions are also observed behind the fuselage and around other parts of the aircraft, generating vertical flow and non-uniform airflow near the aft-mounted propeller. We took the performance evaluation from the UAV based on these main parameters: weight limits, power consumption, and flight metrics. The maximum takeoff weight is around 2,200 grams, while the empty weight of the UAV is about 1,700 grams, thereby providing enough space for payload up to 500 grams. We calculated the total power consumption using the current rate data provided by each component manufacturer multiplied by their projected operating time. We also conduct real testing to ensure the actual power consumption actually matches the estimated requirement. After several tests, we found a much more efficient number, thus changing the total power requirement. In addition, the real flight test also provides us with critical aerodynamics performance data, including the aircraft's minimum and maximum speed, turning radius, as well as the exact takeoff and landing distances. Since several changes were made, there are also changes to the result as well.
To maintain all the components into its position under high vibration and rapid maneuvers, every component is securely mounted to the airframe using a combination of bonded 3D printed beds, mechanical screws, and glove velcro or mesh tape. We add small details in every connection to ensure maximum safety, especially in critical points, such as threaded lock on our tail and slide lock for both wings. We secure both motors using a 3D printed mount, while the cable is safely kept by a precisely 3D printed wrapper. Our UAV is equipped with a circuit breaker which automatically switches off when the current has exceeded the upper limit, preventing the electronics component from smoking or burning out of high current. We test the switch reliability by conducting several manual switches while the motors are running at different speeds, one of which is demonstrated in this video. We also implemented a fail-safe mechanism that, when triggered in conditions such as connectivity loss, immediately commences a right roll, pitches the tail up, and stops the motors.